Welcome to this lecture on the design and simulation of heat exchangers. In this lecture, we will try to solve some numerical problem. In the last class, we have solved some numerical problem and we will try to solve the same numerical problem with a different approach. In this problem, it is a cross flow heat exchanger where the hot exhaust gas is being cooled by the water. So, the parameters are already known to us. We know the flow rate, entry and exit temperature of the gas and the water stream, and since the inlet and exit temperatures are known, we also know the fluid properties and that remain constant. It is not changing with the length of the heat exchanger. It is also given the overall heat transfer coefficient based on the heat transfer surface area, and that is equals to UH 100 watt per meter square, and what we need to find out is the hot side or the gas side surface area. Now, before this is both the fluids are unmixed. So, before going into the details of this problem or trying to solve this problem, we just want to mention what is meant by both fluid unmixed, because this will time and again come that some of the fluids are mixed, some of the fluids are unmixed. So, we just want to clarify this one before we go to the next slide, solution. So, in the mixed and unmixed stream fluid, we find that in this configuration we are saying that both the fluid streams are unmixed. Here we have a finite tube heat exchanger where the tube is having this flow, the tubes are separated, this fluid stream is coming from a particular pipe getting distributed to different sides. So, this is not mixing with this fluid or this fluid is not mixing with this fluid. So, they are separated by these fins. Now, for this fluid stream, this is also coming from some other pipe and getting distributed to different individual pipes. So, this fluid is not able to mix with this fluid inside this tube. So, both the fluids remain unmixed. So, now in contrast to this, if we consider this configuration, you will find that this fluid stream remain unmixed because they are not mixing with each other, they are not able to mix with each other, whereas this we have now removed the fins. So, there is possibility that this fluid stream after passing through this one, there is a possibility that they will be mixing up. So, this fluid stream is mixed and this fluid stream is unmixed. So, depending on the situation, we may have both the fluid streams unmixed, some fluid stream mixed and some fluid stream unmixed, and accordingly the epsilon NTU relation or the NTU epsilon relation will change, and that you have to keep it in mind. So, this problem talks about the both fluid unmixed condition. Now, in this approach earlier for the solution of that problem where both the cross flow fluid heat exchanger with both fluid stream unmixed, we tried to solve by some method, and now we are trying to solve it by F-LMTD relation, because since this is the cross flow heat exchanger, we know that we can correlate this heat exchanger heat transfer by overall heat transfer coefficient and the area product multiplied by the F factor and the delta T log mean temperature. So, in this case what is known to us? Both the entry and exit temperatures. So, if we look at this temperature profile, we will find it is a cross flow exchanger. So, the temperature profiles are not actually known to us, but we assume it to be as if this is a counter current exchanger, where the hot fluid stream is entering from this end and moving out at 100 degree centigrade, whereas the cold fluid is entering at 35 degree and moving out at 125 degree centigrade. Had this been a counter current exchanger, we would have easily determined the log mean temperature difference by say delta T of the larger one minus delta T of the smaller divided by log mean of delta T large by delta T small. This we have already learned, and here in this case actually we know all this temperature, exit temperature, but this is in a counter current configuration. Our heat exchanger configuration is basically a cross flow exchanger. So, we cannot directly use delta T log mean, we have to multiply this one with the correction factor A. So, how to determine this correction factor? Let us see. We know already the amount of heat getting transferred, because we have been told about the mass flow rate of the cold fluid. We know the Cp of the cold fluid and the exit and inlet temperature of the cold fluid stream. So, the total heat is known in this equation. We also know the delta T log mean, and so that we can easily find out to be 111.7 degree Celsius. This is THI, that is 300, TCO is basically 125, THO is hot outlet, that is equals to 100, and TCI, that is equals to 35 degree centigrade. So, and accordingly this hot inlet is 300 and cold exit is 125. So, accordingly if we put this value, we will find delta T log mean as 111.07 degree centigrade. So, now if we go look into this calculation of the F factor, we have to look for the F factor or the correction factor for this configuration, where both the fluid streams remain unmixed. So, in our configuration we have been told that both the fluid streams are not mixing with each other. So, accordingly we have to identify, and we find that when both the fluid streams are unmixed condition, this is the configuration of the, or this is the chart which will tell us the correction factor as a function of R and P. These are the two parameters. What is R? R is basically the hot inlet minus T hot exit, and this cold exit minus cold inlet. So, basically this is nothing but the capacity rate ratio, that is R. And how do we find it out? This is, if you look at here, this P is T0 minus Ti divided by capital Ti minus small ti. This small ti is basically the cold fluid, and this is the hot inlet, hot exit, cold inlet and cold exit. So, this we have written T0 as TCI here, and cold inlet is written as TCI. This is nothing but TCI, and this is TCO, and this is THI minus THO. So, accordingly we find that there are two parameters, one is R and the another parameter is P. P is TCO minus TCI divided by TH inlet minus T TCI. So, T cold inlet is 35, sorry T, if we look at this value, this was 300 coming out to be 100 and this is 35 moving out at 125, if I am correct. So, this is TCO, TCO is 125 minus TCI is 35 divided by T hot inlet is 300 minus TCI is 35. So, accordingly we will find that P equals to 0.34. Similarly, the R value is T hot entry, the inlet is 300 minus T hot exit is equals to 100 and then we have TCO that is equals to 125 minus TCI is 35 and we will find it to be R equals to 2.22. So, now we have to find out for R equals to 2.22, we have for R equals to, these are the R values 0.2, 0.4, 0.6 like that. So, here somewhere this is for R equals to 2 and for P equals to 0.34, here we have 0.3, this is 0.4, in between we have somewhere. So, we can find that somewhere here our value will be. So, accordingly we find that this F factor is 0.85. So, now if we go back to our discussion. So, we have now almost all the parameters known. We know the Q, the amount of heat getting transferred. We already have an idea about the delta T log mean temperature. We have the correction factor A. So, accordingly if we put all these parameters in this equation, we can now calculate the area, because already we have this overall heat transfer coefficient also UH equals to 100 watt per meter square Kelvin, that is also given. So, accordingly we can find out this area to be 39.1 meter square. In our earlier calculation, we got similar, almost similar value of 39.1 or 39.7 meter square, and that discrepancy is mainly because of the we have estimated the friction the correction factor, and so there are inaccuracies involved with that one, and that inconsistency in this area measurement or area calculation is because of that. Now, we will try to solve the same problem, but we will change it to from a design problem to a simulation problem. Like in the earlier calculation, we were trying to evaluate the heat transfer surface area necessary, but in this problem, as if this is a heat exchanger which is already known to us, it is in service, but somehow we have put according to that design calculation, we have estimated the area to be 39.1 or 39.7. So, accordingly we have put or manufactured a heat exchanger, cross flow heat exchanger of area AH equals to 40 meter square, and the overall heat transfer coefficient is still around 100 watt per meter square. And as if now we have changed the hot fluid flow rate, the gas flow rate from earlier value to 1.5 kg per second, and the entry temperature has also changed from 300 to 250 degree centigrade. Now, we want to find out how is the heat exchanger performance or how is the exit temperature of the gas side or the hot fluid and the cold fluid. So, basically it is no longer a design problem, rather it is a simulation problem or the heat exchanger performance problem. So, here what is known is the heat exchanger configuration is known, and what we intend to calculate is the the exit temperature of the fluid streams. Now, if we look, so here as I told you that already we need to already some of the parameters it is known to us. The entry temperature of both the fluid streams are known, the gas flow rate or the mass flow rate of water is also known. The exit temperatures are not known, but we know the heat exchanger configuration and the overall heat transfer coefficient. And it is also, it has already been said that this is a cross flow exchanger with both the fluid unmixed. So, as I told you that the heat exchanger configuration is already known, that means the heat transfer surface area and the heat transfer coefficient is already given. The fluid inlet conditions are known, the entry temperature, and we are assuming that both the fluid streams are assuming, or I mean it is already decided that they will be remaining unmixed, and we want to find out the fluid properties, because this will also be necessary to calculate the heat transfer, and we assume that the fluid properties are constant. So, this has been assumed to be specific heat as equals it is 100 joule per kg Kelvin, and for water it is 4197. So, accordingly we can find out the cold fluid heat capacity. So, that is the mass flow rate of the cold fluid and the specific heat of the cold fluid. So, this is 4197 multiplied by 1 kg per second. So, that will come out to be 4197. Similarly, for the hot fluid, the capacity is mH dot and Cph. So, this is 1.5 kg per second and this is the specific heat. So, it gives us 1500 watt per meter, sorry 1500 watt per Kelvin. So, we can understand that this hot fluid stream is the C mean and this cold fluid stream is the C max or maximum capacity. So, accordingly we can write that Cr is equals to C mean by C max. We can calculate, this will become C mean equals to 1500 watt per Kelvin and this is C max is 4197. So, this will give us Cr equals to 0.357. Now, we have the C mean value with us, we have the Cr value with us, we already said that the heat exchanger configuration is known. So, basically we will try to find out what is the NTU. NTU is equals to UA by C mean, and for the hot fluid stream it is already known UH AH by C mean. What is UH? UH has been given as already its value has been given. AH value has also been considered as 40 and this is we have considered it to be 100 watt per meter square Kelvin, and C mean is this is 1500. So, accordingly we will find that this is giving us 2.67 as the NTU. So, now when we know the NTU, we should be able to ideally calculate the epsilon and from there we will try to find out the other values. So, let us look I mean for this configuration, what are the there are two approaches. Again, we can take help of the chart for the epsilon NTU as it has been shown in the earlier case. I mean when both the fluid streams are remaining unmixed, the epsilon NTU relation can be plotted from this relation, but now we see we have this NTU value known to us. This NTU is 2.67. Now, just now we have calculated it to be 2.67, and from that NTU value ideally we should be able to put this value from this relation in this relation, and we should be able to find out the value of epsilon. Here if we look at the CR value, it is already known, NTU value is already known, and we can ideally calculate, and in reality also we can calculate epsilon, and we will find that this epsilon is coming to be 0.84. We can also take help of this chart and we can fix this NTU. It is somewhere, this is 2 and this is NTU equals to 3, in between this is 2.5. So, 2.67 it will be on the somewhere here. So, if we go up and also we have the CR value known to us, the CR just in the previous slides we have calculated. In the previous slide we have calculated CR equals to 0.357. So, now if we go to this 0.357, if you look at this graph, this is for 0.25 and this is equals to for epsilon CR equals to 0, this is equals to 0.25 and this is equals to 0.5. So, it will be in between somewhere, and we can find out, say, it will be somewhere like this, and here this corresponding value we can see that it will be about this. So, it will be about 0.82, 83 or 84. I mean this is obviously an approximate value we will obtain from the graph, whereas if we put directly this relation in this relation, the value of NTU and CR will directly obtain the epsilon. So, once we know the epsilon, we can try to find out the actual heat getting transferred, because the Q max or the maximum amount of heat that can be transferred in this heat exchanger is also known. We know the minimum capacity fluid, we know the entry temperature of the hot and the cold fluid. So, what is the hot entry? This is 250 degrees centigrade, and the cold fluid is remaining same, that is equals to 35 degrees centigrade. So, we can, and this C min also we have seen this to be 1500 watt per Kelvin. So, accordingly we can try to find out this Q max, and that will come out to be 3.23 into 10 to the power 5 watt. So, when we know the Q max, we can find out the actual heat getting transferred from this relation, because we know the definition of Q is equals to Q by Q max, or this is what is known to us. So, we know already epsilon we have calculated, we know the Q max, we can find out the actual heat transfer. So, that we can find out to be 2.71 equals to into 10 to the power 5, assuming a value of epsilon equals to 0.84. So, when we know the actual heat getting transferred, so it is now easy for us to calculate the exit temperature. The hot fluid stream is, I mean, for both the heat transfer, the C multiplied by the difference in temperature and Ch multiplied by, this is nothing but Ch multiplied by the difference in temperature, and this is Cc multiplied by the delta T C, this is Ch multiplied by delta Th. So, in this equation what we know is this Q already we have calculated. So, this Q is known. We know the hot inlet temperature, entry temperature, the mass flow rate multiplied by Cph is already known, and accordingly we will find that the exit temperature is 69.3 degrees centigrade. And the cold exit temperature will be related again, from this relation. If we just manipulate, we will find that the exit temperature is related by this equation, where on the right hand side parameters are known, Q, Tci, Mc, Cpc. So, we would be able to find out the exit temperature of the hot fluid stream, of the cold fluid stream. So, now we can see that depending on the configuration or the operational parameters of the heat exchanger, we may have to adapt different techniques for solving different kind of problem. It may be a design problem to find out the heat exchanger surface area or the details of the tube or the fin configuration, though we have not encountered the fin. So, but we also the same problem when we have designed the heat exchangers, we may have situation that some of the parameters or some of the operating conditions will change, or with the time, or deliberately we are forced to change the operating condition, and how the heat exchanger performance is varying with with that change in the operating condition is an interesting parameter. So, that design problem now will become a simulation problem, and as we have seen that we have designed a heat exchanger where the operating parameter has been changed and the flow rate of the hot fluid has been changed to 1.5 kg per second, and now that has changed the exit temperature to 69.3 degrees centigrade, whereas the cold inlet condition exit temperature has now come to 99.6 degrees centigrade. So, depending on the heat exchanger configuration, whether they are mixed or unmixed, whether it is a simulation or it is a design problem, we have to take help of this F-LMTD, or we have to take help of that LMTD, or it may be an F-LMTD, and we have to look for the appropriate equation to solve that correction factor F, or we have to find out the appropriate, or we have to take help of the appropriate chart and for calculating the correction factor, or the that R or the P parameters, and accordingly find out the heat transfer, or we have to design parameters. Thank you.